This is Activity 9 for Chapter 18, EAS. The general idea of these reactions are nucleophilic attack towards an electrophile and an elimination reaction to regenerate aromaticity. For Part 1, Friedel-Crafts alkylation, we need to draw the lone pairs and identify each transformation as either nucleophilic attack, loss of leaving group, proton transfer, or rearrangement for every step. This is Friedel-Crafts alkylation, so we need to make an electrophile first. To do this, the alkyl halide will do a nucleophilic attack on the AlCl3. Then there will be a loss of leaving group, which is the AlCl4, to create an electrophile, which is a carbocation. Next, the pi bond on the benzene ring will act as the nucleophile and will attack the carbocation. This will break aromaticity and leave a carbocation on the benzene ring. The AlCl4 that was created in the second step will be used to depronate the hydrogen to restore aromaticity. Overall, the first step has a nucleophilic attack, the second is a loss of leaving group, the third is a nucleophilic attack, and the final one is a proton transfer. Now for Part 2, Friedel-Crafts alkylation. For Part 2, we also need to show lone pairs and identify each transformation. The same idea applies. We need to create an electrophile. First, the acid halide will do a nucleophilic attack on the AlCl3, then the lone pairs of oxygen will make the triple bond and kick out the AlCl4, hence loss of leaving group. Again, the pi bond on the benzene ring will act as the nucleophile and will attack the carbocation. Remember that the attack will occur onto the carbon and not the positively charged oxygen. Finally, AlCl4 will be used to depronate the hydrogen to restore aromaticity. So, same as the first one, you have a nucleophilic attack for the first step, loss of leaving group for the second, nucleophilic attack for the third, and proton transfer for the final. Part 3. Evaluate the mechanism of the above Friedel-Crafts alkylation and acylation reaction. What are the differences between the two cationic species labeled A and B? Which can undergo carbocation rearrangement and which cannot? For the two cationic species, the species A has the positive charge on the carbon. Species B has the positive charge on the oxygen. This means that species A, which is Friedel-Crafts alkylation, can undergo carbocation rearrangement, while species B, which is Friedel-Crafts acylation, cannot undergo carbocation rearrangement. For Part 4, we need to propose a mechanism for the following transformations. So for the first one, you first must notice that this is a Friedel-Crafts alkylation. Then you need to know that the first step should be making the electrophile. So, you use the alkyl halide to do a nucleophilic attack on the FeBr3. Then you will have a loss of leaving group that will give you the FeBr4 and the carbocation. Remember, if a carbocation rearrangement is possible, it will do so to be more stable. Next, the pi bond of the benzene will act as a nucleophile and attack the carbocation, breaking aromaticity and leaving a positive charge on the ring. The FeBr4 will be used to depronate the hydrogen and restore aromaticity. This should give you the final answer. For the next one, you need to see that this is a halogenation. The first step is to make the electrophile. The Br2 will attack the FeBr3. Then, there will be a loss of leaving group that will leave you with the FeBr4 and the positive charge Br, that is your electrophile. The pi bond will attack the electrophile and break aromaticity, leaving a positive charge on the ring. FeBr4 will be used to depronate the hydrogen and restore aromaticity, giving you the final product. Moving on to the next one. You should know that this is nitration. Again, making the electrophile should be the first thing in mind, and for nitration, you need to make the nitronium ion, which is the electrophile. You should start with HNO3 and the acid. The acid is depronated by HNO3. This will give you an intermediate that has two positive charges and one negative charge. Next, the negatively charged oxygen will push the water out, making this step a loss of leaving group. This will create the nitronium ion with a positive charge on the nitrogen. Next, the pi bond on the benzene will attack the nitronium ion, breaking aromaticity. Water will depronate the hydrogen on the benzene, restoring aromaticity and giving you the final product. Remember that you can also write it as NO2 on the benzene ring. For the next one, you need to see that this is sulfonation. Knowing it's sulfonation, you also need to know that you don't need to create an electrophile because sulfonation contains SO3 gas in fume, which is the electrophile. The pi bond on the benzene ring will attack the SO3, which will move lone pairs onto oxygen to neutralize the S from any charge. This also breaks aromaticity and leaves a positive charge on the ring. Water will depronate the hydrogen, restoring aromaticity. The acid created by the step before will be depronated by the oxygen with a negative charge, and this will get you the final product. For the next one, you need to see that you have an acid halide and AlCl3, which means that this is a Friedel-Crafts alkylation. For this one, you need to create the electrophile first. Even though you see the acid halide connected to the benzene ring, you still use the same steps. The Cl on the acid halide would attack the AlCl3. Next, the oxygen's lone pair from the carbonyl will push out a leaving group, leaving you with a triple bond positively charged oxygen, hence the electrophile, and the AlCl4. The pi bond on the benzene ring will attack the electrophile and break aromaticity, leaving a positive charge on the ring. Next, the AlCl4 will protonate the hydrogen from the ring to restore aromaticity and give you the final product. For the last three problems, it is asking you to make a mechanism for the following substituted benzene. For now, you only need to know the mechanisms. Predicting the location of the next reaction will be discussed in the next activity. For the first one, again notice that this is a nitration, which means that you need to make an electrophile, the nitronium ion. Remember that HNO3 will depronate the acid, giving us the intermediate with several charges as before. There will be a loss of leaving group where the lone pairs of the negatively charged oxygen will kick out water, leaving you with the nitronium ion. The next step is using the pi bond of the benzene ring to attack the nitronium ion, which breaks aromaticity. Water will depronate the hydrogen on the benzene ring and restore aromaticity, giving you the final product. On the next one, make sure that you see that this is halogenation because of the Br2. Knowing it's halogenation, this means that you have to make the electrophile. The Br2 will attack the FeBr3, making the electrophile, and the FeBr4. Next, the pi bond on the benzene ring will attack the electrophilic Br, breaking aromaticity and leaving a positive charge on the benzene ring. The FeBr4 will deprotonate the hydrogen from the benzene ring, restoring aromaticity and giving you the final product. The last problem includes an alkyl halide, so this has to be Friedel-Crafts alkylation reaction. And as before, your first step should be making an electrophile. So the alkyl halide will attack the FeBr3. Then the loss of leaving group occurs, leaving you with a carbocation and FeBr4. Again, you need to recognize that you can do a carbocation rearrangement to get a more stable cation. The pi bond on the benzene ring will attack the carbocation, breaking aromaticity and leaving a positive charge on the ring. FeBr4 will depronate the hydrogen on the ring to restore aromaticity. This gives you the final product.